How's everybody? Excellent. 2 thumbs up. Can I get a couple of thumbs? Amazing. Well, welcome to the session. The awesome session titled Making Acquaintances with Exotic Encoding. So we're making lots of acquaintances right now, and now we'll make acquaintances with exotic encodings. And my job is just to do a quick introduction of our speaker, our amazing speaker today. Our speaker, his name is Trapsilo Bumi. He's come all the way over from Tokyo today to give this talk, which is awesome. And Bumi is a software developer for HENNGE. So that's on me, sorry guys. Henge, based in Tokyo, and he's passionate for all kinds of tech and always exciting challenges, whether it be building software solutions or sharing it with others through talks, like he's doing right here. And when Bumi's not coding, he can be seen traveling, board gaming, or playing and conducting the Anglung, the Anglung. Oh my goodness. Sorry guys. So can we all get like a really warm round of applause for Bumi?
Test. Okay, thank you for the introduction. My name is Bumi, and I'm from Henge, which is based in Tokyo, Japan. So first of all, slides, okay. A little bit about me. I'm from Indonesia, and here, I'm currently a software developer for Henge, which is based in Shibuya. It's a B2B cloud security solutions company, and it also has a cool internship program. So if you're looking for internships, or if you're just looking for a new job, just go and visit this URL, and we have a challenge for you waiting. Okay, so let's get right to it. First of all, before talking about encoding, let's revisit a little bit about what encoding really is. Has anyone ever seen this picture before? Or this table? Wow, cool. One over there. So this is probably arguably the world's first encoding ever. It's basically the telegraph table that defines how to encode the letters of the English language into numbers. So that's what encoding basically is. It's how to transform letters, which are not numbers, into numbers. So here we can see how the letter A is, there's some symbols over there that tells you which keys to press in the telegraph. This is also another example of encoding, basically. So it's the Braille code, as you probably know. It also transforms letters into symbols, in this case, which are dots on a 2x3 grid. And they are divided into what are called decades. And yeah, so this is also another example of encoding. When I was browsing Reddit, I saw a great Eli 5, which someone was asking like, why am I seeing these strange symbols in my word processor? And this guy explained it very well in several sentences. Computers store everything as numbers, right? And letters are not numbers. So to fix this, we agreed upon ways to encode letters as numbers. So encoding is basically how to transform letters into numbers. So US ASCII was one of the first successful standardized mappings. So we needed a way we needed to agree on a way of how to transform these letters into numbers that can be read by different machines. So the US ASCII was invented then. And then, after that, different standards was created by different people around the world. Those countries were extending this code that was already established into ways that can accommodate their own language. So for example, the Spanish people made up one code page that extended ASCII with their own diacritic letters, and for example, the Greek people also created some another encoding which accommodated their letters, and so on and so forth. But this created what I call bilingual encoding. So these encodings only accommodate their language and English. They didn't need to support other languages other than their own language. And because it was based on ASCII, then automatically it supports English. So these encodings were not by nature multilingual. So then some people thought, well, the internet is bound to be used by everyone around the world. So we need one way. We need to agree on one way to encode all of these letters of the world, all of these languages that have different kinds of glyphs into one standard that we can all use. So then the Unicode standard was created to unify those encodings. So here there's a unique concept called code points. So Unicode doesn't actually transform the letters themselves into numbers, but first they assign the letters into specific code points, which are numbers. Those code points are numbers, and then those numbers are transformed into bits. So there's a little intermediate there between the concept of the letters themselves into what we send, which are bits. So and then the Unicode standard leaves the visual rendering to each software. So it doesn't dictate that this letter has to appear like this or this letter has to look like this. It just defines the concept of a letter, like for example the letter A in the Latin alphabet, and assigns it into a specific code point. Like for example the code point U46, for example, and then that 46 is converted into bits depending on which width you want to use. So the width of the bit sequence is called the code unit. And so in this table, for example, you can see that the letter A can be represented by at least two different types, right? There's the printed A and then there's the handwritten A. And Unicode doesn't care about those two different types. It just cares that what you see there is the letter A. And then it encodes it into a specific code point. It assigns the letter A to U plus 0061. And then, okay. And then the 61 can be encoded differently depending on which byte width you want to choose. For example, in U2F8, it can be encoded as the byte 61. But in U2F32, it can be encoded differently. And then for other letters, like for example, the sharp S or the kanji for east or this exotic letter, it can be encoded. It can be just assigned into a code point, and then that code point can be transformed into bits. So how do we do it in Python? So in Python, as you already know, there are two types of strings. There are text strings or Unicode strings, and there are byte strings, or in the documentation is officially pronounced as text sequence and binary sequence. What are these actually? So the text sequence is actually a sequence of Unicode points. As I explained before, they're not actually letters, but they're actually just code points that are assigned to a concept of a letter. And then the byte streams themselves are actually just a sequence of bytes. So you can know that these sequences don't necessarily have the same length, even though they encode the same information. For example, here you can see that in a text string or a Unicode string, you can put all sorts of symbols in there, and then it will work fine because those letters there are just code points in the Unicode. Whereas in a byte string, those letters aren't actually letters, but they are just bytes that we represent as letters. So the first string there is actually a sequence of bytes. So to convert between one another, we use the functions decode and encode, which we can call directly on those sequences. So if you want to transform bytes into strings, then you can use the decode function. And then you supply the 2 parameters. And if you want to transform the string back into bytes, you use the encode function, which you supply those 2 parameters, and then it transforms those code points into bytes. So the first parameter is encoding, which dictates how you want to transform those code points into bytes. And then the second parameter is how to handle a case where those code points aren't recognized, or this particular sequence of bytes aren't recognized as a valid code point. So it's pretty simple at a glance if you want to handle encoding, right? So let's take a little look at how Unicode is used in the wild. So we'll probably ask ourselves, right, like, who in the world doesn't use Unicode? In the survey by w3text.com, UTF-8 is used by 93% of the websites. But then there are the 7% of websites that don't use Unicode. Like these encodings that you see here are still used by a small percentage of the internet. And so even if we like to think that Unicode is ubiquitous and used everywhere, like if you scrape around a website and you'll expect for that website to use Unicode, then probably you will be sometimes wrong. And those websites will use this different encoding. This is an interesting graph from Google about how Unicode has changed over the years. So from the early days of the internet, we can see that Unicode wasn't recognized in the first place. But as the internet grows, the usage of Unicode also grows. And at 2008, it surpassed the usage of old encodings like ASCII and Windows Latin and the other Chinese and Japanese individual encodings. But yeah, this graph shows us that Unicode wasn't the standard from the beginning. And Unicode is still a journey to take for some countries to change their initial encoding from something that they invented themselves into the standard that everyone accepts. So who hasn't seen this error? Like this error is pretty, for people who handle text, you see it quite a lot. So blah, 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 codec can't encode character, blah, 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 in position, blah, blah, blah. So this error is basically like telling you that I can't recognize this character, this code point. I don't know how to transform this code point into the sequence of bytes. Or if you reverse it, like Unicode decoder, then it's telling you that I don't recognize this sequence of bytes, and I don't know how to transform it into a valid code point, a valid Unicode code point. So here I want to show you the example of some real-world examples of how Unicode is not used as the standard, which is emails. Because in the experience of my company, we handle emails a lot. And we often run into this problem because we're a Japanese company, and sometimes Japanese companies don't recognize or follow the standard. And we run into these problems where they still use the Japanese old encodings. So why is this happening? It's because RFC 821, the RFC that formalizes the SMTP protocol, it dictates the use of ASCII as its transfer format. And using non-ASCII characters in an email, it requires SMTP extensions. So SMTP initially didn't support using those characters outside of ASCII. And then we needed some workaround to still use SMTP but transmit non-ASCII characters or letters. So then RSA 5321 was created. But still, many email clients, they don't recognize and they still don't use Unicode as the default, which is why some clients, some companies still don't use Unicode. Maybe not on purpose, but unknowingly, the employees of this business still use old email clients that don't provide Unicode as the default. So this is one kind of a problem that we see often that sometimes makes it difficult to handle emails in a straightforward way. So we needed some tricks to work around those encodings. So what kind of encodings are not Unicode exactly? One example is this, ISO 88591 or Latin 1 or CP819. It has a lot of names. But basically, it's the basis for the most popular 8-bit character set. So if you need an 8-bit character set and you created this before the Unicode standard was implemented worldwide, then you'd use Latin 1, which is also the basis for several popular languages. Several of the most popular languages in the world this is accommodated by this encoding. So that's why this is so popular. And the default encoding for these documents, this is the default encoding for the documents that are delivered via HTTP and have the MIME type text/something. So it's the default of many things, which is why it's so popular. And then there's Windows 1252, which is used by the default legacy legacy components for Windows. Why this is popular is because, well, one of the products of Windows or Microsoft is Microsoft Office. People use Windows, obviously they use Microsoft Office. So this is why it's so popular, and it's used in still a lot of emails. Like if you use Outlook, then probably Outlook still uses this encoding. And this is one of the this is the official standard for the People's Republic of China. So they don't actually recognize Unicode, but they made their own character set, which is Unicode compatible. And it's called the Unicode transformation format. And it supersedes another standard created by them before Unicode, which is GB 2312. This is another encoding which is popular in countries other than China, which is Taiwan, Hong Kong, and Macau. It was created in the 1980s, so before Unicode was implemented everywhere. And China also used this before they created their own standard, which is the GB something something standard. This Big 5 encoding is also used by a lot of organizations, extended by Microsoft, by IBM, by other companies. So it is quite popular too. And then this is the popular encoding used in Japan called ShiftGIS. It's developed by the ASCII Corporation, which is quite a funny name. And it is also one of the prominent Japanese character encodings that they used before Unicode. And then there's also other encodings. I could go on about this forever, but I just wanted to show you that there are a lot of encodings that people still use other than Unicode. So how do we handle this in Python? First of all, obviously the first thing we do is use the codex package, right? We just call encode or decode function on the string that we want to convert to bytes or the bytes that we want to convert to string. We can choose between 3 error handling parameters, which is, do we want to skip this, or do we want to raise an exception if we can't recognize the code point, or do we want to replace the unknown code point with something else, like that symbol there, which you sometimes see if there's a mistake in the encoding. But what if we don't know the encoding for this text? Or there is a specified encoding, like for example in the HTML document, they specify the encoding, but it doesn't match, or it spits out characters that we can't see, or jumbled characters, or what Japanese call mojibake. Or maybe there is just no way to specify the encoding in that document or file or whatever. So it's not an HTML document, it's not an email, it's something in the file system created by an application that just doesn't specify the encoding. It happens a lot in, for example, in scraping websites, in reading or parsing email. When you open the attachments don't specify what encoding they use, and, well, we have to guess. So there's a package in Python called cardet. It's a character encoding auto detection library, so it's based on the universal cardet project by Mozilla. It basically uses heuristics to map common patterns into a specific language. Not the encoding, but the language. But then that language usually uses a specific encoding, so we can guess the encoding with a certain confidence. But we don't know for sure 100% if that's the encoding used, but it's better than nothing, right? So is cardet the answer to everything? Well, I would say no. We only use it as a last resort. We don't need to use cardet in the first place, but we have to try first. For example, if it's an HTTP transfer document and there is no charset parameter in the content type header, if there is, then we should use that because they are telling us that that's the encoding used, so we don't need to guess, right? Or if it's HTML and there is a meta tag in the HTML document, then we should use that encoding specified because that's what they tell us. The encoding, that is the encoding that they are using. Or it's XML and there is no encoding attribute in the prologue of the XML part. So cardet is not the answer to everything. We shouldn't use it in the first place, but only use it as a last resort. But then cardet itself is not perfect. It can spit out some encodings that aren't even in the Python standard library. For example, you see Taiwan. So, and also it sometimes has a confidence rating that is very low. It's based on heuristics, so it's not perfect. It sometimes fails. It sometimes fails to guess the encoding. So the best thing to do is to set a threshold. If it's below the threshold of the confidence, then you should try other methods or just don't try to transform it because it will spit out jumbled characters anyway. Then there's the last resort, which is using a static table, which is based on the experience of your organization. In this case, my company collected a lot of weird encodings in the emails that they specified. And like, for example, some emails mean CP932, but they write these lot of different things, which mean just one thing. Also, like, for example, U2F8 in the email can be specified as U2F8 Mac, U2F8 Docomo, U2F8 KDDI, U2F SoftBank. Like, each operator basically has their own encoding, which is basically U2F8, but maybe they use the private space for their own stuff like emoji or something. So in summary, encoding is important for us to understand if we want to process text in a lot. So we should keep some tricks up the sleeve for handling exotic character mappings, for example, the cardet package. If we can't find, first of all, if we can't find the encoding that is specified in the document itself, then we should use cardet. But then if cardet fails, then we fall back to the last resort, which is a static list that we keep based on our experience on collecting documents or emails, and then which one works, we just try it, and then if it works, then we just keep that static list for processing the next documents that we find. Okay, that's all from me, thank you. And if you want to access the slides, they are available here.
Thank you so much, and awesome that Bumi just went through the presentation whilst AV happened. Like that was absolutely epic. We've got about 5 minutes for questions, so does anybody have any questions? Yeah, Don, awesome. Anybody have any questions? I got a question, and then hopefully somebody else will have a question. So I'm just curious as to what the success rate is. Like, I loved how it was like last resort, last resort. Like that's definitely like practice, right? I'm just wondering what the success rate is typically with, like, you know, a corpus of emails, whatever else that you'd find. Like decoding success rate, like just using all these packages.
Okay. So well, I would say when you look at the encoding that is in the document, then it's probably about 70%, I would say 75% of the documents just encode correctly. But 25% of those documents don't, so we need to use cardet. And then the success rate of cardet is pretty high. Maybe if you feed like 100 documents, maybe 98 would come out as correct, I would say. But there are a small percentage of documents that even cardet can't guess. So for example, those weird extended encodings that you need to keep a static list of, that's why it's the last resort. Yeah.
All right. Epic. Amazing.
So from the statistics you showed, it looks like UTF-8 is taking over the world, or at least the internet. Is there ever a good reason not to use UTF-8 other than making your job harder?
You mean UTF-8 specifically or Unicode in general?
Either.
OK. So there are reasons you don't want to use UTF-8. What I mean by that is you probably want to use UTF-16 or UTF-32, depending on whether you use those exotic characters a lot. Because if you just use the English language, then UTF-8 is fine. But if you want to use other languages that are far away in the Unicode mapping, then probably it's better to consider using a 16-bit width or a 32-bit bit width. But for non-Unicode, I can't imagine why you would create new documents with non-Unicode encoding. The reason they exist is because they were created before Unicode existed. Like the programs themselves that generate the documents didn't recognize Unicode back then, so that's why they exist. But now, like in the current age, you should use Unicode everywhere.
OK, thank you.
Any more questions? All right. Well, maybe just one more round of applause then for Bumi for an excellent presentation.
Thank you.
And here you go.
Oh, thank you.
Thank you.